Hello, everybody. Thank you for coming to DataXday online conference and welcome to our very last day of this 1-month online conference. So today, for this very last talk, we're welcoming Olga Petrova, a deep learning engineer at Scaleway, who's here to tell us about semi-supervised deep learning with GANs. So thank you very much, Olga. You have the floor.
Thank you for the introduction. Good evening, everyone. So I'm a machine learning engineer at Scaleway, a French cloud provider, and today I will tell you about semi-supervised machine learning with generative adversarial networks. So my talk has two main parts. The first part is theoretical. I will start with an overview of semi-supervised machine learning and how it is different from supervised and unsupervised machine learning, which are topics that I think more people are familiar with. Then I will present the architecture of generative adversarial networks, which was originally actually an unsupervised algorithm. And then we'll move on to how to actually do semi-supervised learning with GANs. Finally, for the practical part, we'll have a tale of cats and dogs, which you can probably guess is a classification problem. So semi-supervised machine learning. Well, let's first say a few words about what it is. So we're probably all familiar with unsupervised learning, which is the type of machine learning that involves unlabeled training data. So some examples of algorithms that are most frequently used are clustering, which is when you look at your data points that don't have any labels, and you just put them in little clusters, depending on how close they lie to each other in their feature space or latent space. And also generative adversarial networks, which can be used to generate new data that has the same distribution as your original unlabeled training data. Then there's supervised machine learning when the training data is labeled. The most common tasks, I suppose, are regression and classification. And you may have noticed that here I made the distinction between the two mainly based on whether the training data is labeled or unlabeled. And I will do sort of the same thing for semi-supervised machine learning. Here, there are actually two types of training data. There's a subset of the training data that is labeled, and then there's the rest, which is typically a much larger part, that remains unlabeled. However, the task itself is normally of a supervised learning variety. So for instance, it could be a classification task, even though you're using unlabeled data or partially using it. So we have discussed, well, we have a very rough idea of what is semi-supervised learning, but why should we bother with it? So first of all, most practical tasks today actually come from supervised machine learning. And here there are some good news. So the good news is that today's supervised models are actually extremely powerful. There's some very impressive results. However, many of these very impressive results come from very large or rather very deep artificial neural networks. And of course, the larger the network, the more trainable parameters it has. And here comes the first bad news. So the larger the model, the more data it needs to be trained. And the really bad news is that labeling data remains expensive. So this is something that often has to be done manually by human experts, which of course doesn't scale very well. And the situation is even worse for highly specialized fields, such as medicine, for instance, when you could have multiple medical doctors manually examining, let's say, images, thousands of images, and trying to label them like that. Unlabeled data, however, is much more readily available because it is, well, typically much cheaper. And semi-supervised learning is a solution that proposes to use this unlabeled data in order to boost the performance of a supervised machine learning model. So hopefully this answers the question as to why would we do semi-supervised learning. And now I want to say a few words about the big picture of how it works. So here we're going to consider a classification task, but a very, very simple one to start with. So let's say this image here with the two rings, that's our data set. So our feature space is only two-dimensional. They just can be plotted as dots on a plane. And there are two classes here. There's well, we'll just call them blues and oranges for obvious reasons. So this, of course, is a very simple classification task. Whatever is on the inner ring is blue, whatever is on the outer ring is orange. However, let's say that we only had a few labeled training data points. So something like this. Now, if this is all we have as far as labeled data goes, then we are actually in trouble if we try to do supervised machine learning. Because let's say now we want to figure out what is the label of this point here on the upper right. And if we don't use the unlabeled data, so the unlabeled data are the little points that are grayed out. If we don't take them into account and we try to imagine where would the decision boundary between the two classes lie, we could think of something like this. So let's say that's the boundary between oranges and blues, which of course would mean that this point here is blue. But if we look at the original fully labeled data, we know that that's not actually correct. So we are wrong here. However, if we do consider the unlabeled data points, it is very easy to see that the data distribution forms two rings, and then, the two rings. And then we can use the labeled data points to assign a class label to each of the rings. So then our decision boundary might look more like something like this, which of course makes more sense given what we know. And then we can assign the correct label to this data point that we were curious about. So that makes us happy. Right. So overall, the main idea of semi-supervised machine learning is that the unlabeled points give us information about the data distribution that we're dealing with, and then we can use the labeled points in order to assign class labels. Now we'll move on to generative adversarial networks, this GAN architecture. So I provide a few references throughout the talk. So here's the reference to the original GAN paper by Ian Goodfellow and company from 2014. So the original GAN was meant for unsupervised machine learning. So the training data would be unlabeled, and for instance, it could be MNIST images, such as these ones. The goal is to simply generate data that matches the distribution of the training data. Or in other words, we want to learn how to produce images from scratch that look like handwritten digits. So they don't come from the data set, but they look like MNIST digits. In a GAN architecture, there are actually two networks. There's the generator and the discriminator. And the generator is a deconvolutional neural network. So this is something that is going to generate an image from random noise. And just in case you're not familiar with deconvolutional networks, it is far likelier that you're familiar with convolutional networks. So just make a little comparison. So most image classifiers involve a convolutional network, and a convolutional network is basically the inverse of the deconvolutional network. So in a typical classifier, we would take an image, so let's say the image of this 8 here, and we would pass it through the convolutional neural network that would, let's say, reduce its size at every layer. You can think of it that way. And then in the end, we would arrive at a one-dimensional array per image that would basically contain the class probabilities for the different classes. So that's the convolutional network. In a deconvolutional network, we have the same process, but in the opposite direction, meaning that we start with a vector. So in this case, we start with a vector of just random noise, just to introduce some randomness into the system, because we don't want to generate the same exact image every time. So we start with this noise vector, and then we're going to pass it through deconvolutional layers. And when you pass something through a deconvolutional layer, instead of kind of decreasing the size of your image, you will actually be increasing it. So in the end, you will arrive at this fake image that you have generated. So that was the generator. And now there's also a second network that is called the discriminator. Now for the second network, there are two types of data that it has to deal with. There is the so-called real data, which is whatever comes from the training set. And then there's the fake data, which is whatever has been generated by the generator. And the discriminator itself, here the idea is actually very simple. It is just a binary classifier. So for images, it would typically be a convolutional network. And this is a binary classifier that is trained in a supervised way. We assign the real label to all of the images coming from the training set, and we assign a fake label to all of the images produced by the generator. Right, so training it is pretty straightforward. There's just supervised binary classification for real versus fake. As far as training the generator goes, this is actually where it gets much more interesting. So as I said, the generator is going to produce an image given some random noise. So basically at every training epoch, you would just generate a new random noise vector. Once you produce an image, you're going to take that image and pass it through the discriminator. And of course, this generated image depends on the weights of the generator. So you can do the gradient in the end. So you pass the generated image through the discriminator, and then it is either accepted as real or it is rejected as fake. And in the event that it gets rejected by the discriminator, you want to modify your generator in order to produce a better image next time. So actually, the objective for this whole process is for the generator to get good enough that the discriminator wouldn't be able to tell the difference between what is real and what is fake. So for the unsupervised GAN, your final product is the generator. So the discriminator is just a network that you keep around to train your generator, and then you throw it away. And this is going to be different to the semi-supervised case that we'll talk about later. So here I have a very slightly more mathematical description of what is happening. So if you're not into that, don't worry about it, but otherwise we'll just go through it kind of quickly. So we can say that real data comes from a certain distribution, and our task is to have the distribution of the generated data match that of the real data. So the discriminator is trained to assign the correct label, is it real or is it fake, whereas the generator is trained to basically fool the discriminator. Now, here I have the loss function for the GAN, and again, you don't have to worry about it too much, but if you're used to seeing binary cross entropy, you can see that this is actually just binary cross entropy. Okay, so it's missing the overall minus sign, which is why you have the mean and the max, which would normally be in the reverse. But basically, the discriminator wants to minimize the binary cross entropy because it wants to assign the correct labels to the data, whereas the objective for the generator is actually the opposite, but it is only the opposite for the fake images. So for the fake images, it actually wants them to be accepted. Okay, so the next thing I wanted to mention was, well, how good can these generative adversarial networks get? They can actually get quite good. So really, really good, actually. There is this semi-famous website, thispersondoesn'texist.com. And every time you go to the website, you get a new picture of a person. So that's one picture, and then next time you get this one, and then you refresh. So all of these images that look pretty realistic, at least to me, the thing that is a bit creepy is that these people actually don't exist. So all of these images have been imagined by a generative adversarial network that has been trained on, I'm not even sure how many images of real people. So it really does get quite good, this unsupervised GAN. And well, good for the unsupervised GANs, but the next question is, how can this help us in semi-supervised machine learning? So this is the next part. Okay, Okay, so what is the basic idea here? I will keep referring to this example with the 2 circles. I know it's a bit of a boring example, but I just find it very illustrative. And again, there are some references if you want to learn more about what I'm talking about. So here our data, well, our data in general has a certain distribution. So in this example, our data forms 2 rings, particular radius. Radii, and then the task of the GAN is to attempt to learn that distribution. So what it means is that the generator will be trained to produce points that form the 2 rings. And then the few labeled data points that we have can then be used to assign the class labels. So is it a blue ring or is it an orange ring? And then again, the advantage of this is that without the unlabeled points, we wouldn't be able to draw a very good decision boundary between these 2 classes, whereas if we realize that there are 2 rings, we have a much better chance of actually classifying the data correctly. Okay, so we already talked about the unsupervised GAN that comes with a generator and a discriminator that is trained to discriminate between real and fake. Now, in a typical supervised image, or whatever, actually, not just images, classifier, we would have k classes as the output. So here we have just 2 classes, blues and oranges. In a semi-supervised GAN, we are going to replace our discriminator with a classifier. However, it's not going to be just a simple supervised classifier that we would normally use. It is actually going to be a classifier with an added new class, so with k+1 logits at the output. Now, the first k classes are real, so real in the sense of GAN, and the added k+1 class is fake. So now we have 3 classes, blues, oranges, and fakes. So the semi-supervised GAN in the end is made up of a generator, which is exactly the same generator as we had for the unsupervised GAN. For images, it's just going to be a deconvolutional neural network. And this new discriminator / classifier. So I will kind of use the 2 names for it interchangeably, but it's the same network. So actually something that I want to mention here is that for the unsupervised GAN, it was the generator that we were mostly concerned with. And here we actually don't care about the generator. It is just helping us train our classifier. And in the end, our product is actually going to be the discriminator. So how are the networks trained? Here's when it gets, again, a little tricky, because now we're dealing with 3 kinds of data. There is labeled data, so these few labeled points in our example. There's also the unlabeled data, so all of these points that are grayed out. But then in addition to those 2, we also have data that has been generated from noise vectors by the generator network. Now, the discriminator has to deal with all 3 types of data, and it has to deal with them differently. So first of all, it is trained to assign the labeled data to correct classes, so blues to blues, oranges to oranges. Now, the unlabeled data just has to be assigned to one of the real classes. So it's blues or it's oranges, but we don't know which ones, so we don't care. The generated data, however, has to be assigned to this new fake class. And then finally, the generator is again trained to fool the discriminator, and the objective there is to get the generated images to be assigned into one of the k real classes. So again, blues or oranges, but it doesn't matter to us which ones. And the hope, which ends up working out in the end, the hope is that through this process, the discriminator will learn to place the unlabeled data that we have into correct classes, and we'll also learn how to do it for the data that it has not seen before during training. So one thing I wanted to discuss, which I found a little surprising, although in retrospect, maybe I shouldn't have been so surprised. So as I said, the generators from the unsupervised GANs can produce very impressive images. So we have seen some examples of those. However, the GANs that are used for semi-supervised machine learning actually do not. They don't produce very good images at all, and there's a good reason for it. So now I will give a kind of hand-wavy explanation of a much more rigorous one that comes from this paper that I have a reference to, the paper from 2017. Basically, the point there is that in order to get a good classifier, the generator should be bad. So by bad, it just means that instead of generating images that look real, it should generate images that are complementary to the real ones in feature space. So this is, I think, most easily seen with our two-ring example. So here, our feature space is just two-dimensional plane. So the complementary points to the real ones would be whatever lies outside of the two rings. So in between rings, inside the inner ring, outside the outer one. That's the complementary space. Now, what is the reason for why we need a bad generator? Well, if you look at this image with a bunch of grayed out points, it shouldn't be too hard to convince yourself that actually adding more grayed out points to build a stronger ring, that really wouldn't help us so much. What would help us, however, is to generate some points in between the two classes, because if you generate points in between the two classes, it will, in the two rings, it will be easier for the discriminator to tell that whatever is on the inside of that, the fake ring belongs to the blues, and whatever is on the outside belongs to the oranges. So in other words, we get a sharper decision boundary. So this point is kind of subtle, but I think it's kind of interesting, and we'll get back to that once we move on to the practical part. Oh, speaking of the practical part, so there it is. Well, okay, so I will actually go to my GitHub now. So in this repository, I have, I have the slides, links to the blog post where I talk about all of this semi-supervised learning, etc. But also have a notebook with a PyTorch implementation of a semi-supervised GAN. Okay, so since the title of this part is A Tale of Cats and Dogs, you probably wouldn't be surprised to see some images of cats and dogs here. So the task that I'm trying to solve is the famous cat versus dog classification. And I just wanted to show you a few images to demonstrate that this is not a completely trivial task. So some images feature multiple animals, and some images there's also human present. Some are outside, some are inside. There are some obstructions. And now what we're going to do is we're going to try to learn to classify the images based on only 100 labeled pictures. So 50 dogs and 50 cats, which of course is not much. And to get the, well, there's of course the random benchmark, the 50%, which is randomly choose them. But the next best thing we can do is to train a regular supervised model on these images. And I just wanted to pick some sort of standard architecture, which is, of course, an overkill for the 100 training samples, but I chose the ResNet 18 to be trained on this 100. And then I tested on a balanced test set, and the accuracy is 60%. So not much more than 50, but okay, that's unsurprising. So what I'm going to do next, I'm going to run a semi-supervised GAN where I have a generator that is a pretty simple convolutional network. And I will keep the same exact architecture for the discriminator. So we had a ResNet 18 classifier before. We still have a ResNet 18 classifier now. And I just want to stress that this model has not been pre-trained, because of course, if it has been pre-trained, then 100 images is plenty enough. So we still have 100 labeled training samples, and we now have 30,000 unlabeled images. I think they're about equally distributed between cats and dogs. Okay, so here again, I won't actually, won't dwell on the code too much. If you're curious and if you like PyTorch, feel free to check it out. But basically, after just 13 training epochs, we have already reached 72% accuracy. So not bad. I mean, this was done in just a matter of minutes. And let's see, right, after 40 training epochs, I was able to go from 60% for the supervised benchmark to 83%. So there's an over 20% increase in accuracy on the test set. Now, something that I also wanted to show here is, when I was talking about these bad generators that are supposed to produce images that are complementary in feature space, of course, it is clear what complementary means for our two-circle problem, but what does it mean for cats and dogs? Apparently, it means something like this. So if you look at the images here, they're not quite cats, they're not quite dogs. They seem to feature very weird cat and dog body parts. So this is the kind of generator that it takes to produce a good classifier. So far, this tale has not been, very good as far as tales go, perhaps. And that is because, in my opinion, every tale should come with a moral. Or, in other words, this tale should be a cautionary one. And indeed, there are two things that I learned in the course of implementing this project that I wanted to mention. So the first moral of the story is that the choice of your labeled data actually matters a lot. This, again, in retrospect, it seems obvious. Of course, if you have very few labeled points, of course, the fewer labeled points you have, the more the choice of them matters. So if you have very few labeled data points, your results will differ a lot based on which images you chose to label. So one thing I did was I averaged the same experiment over, I think about 10 different runs where I randomly chose 50 dogs and 50 cats. So the average increase in accuracy over the supervised benchmark that I got with the semi-supervised GAN was only 10%, versus what I refer to as a curated label dataset, where I chose the more representative images, which is where I got the improvement of over 20%. So what I mean by representative here is I basically took out the images that, took out and replaced the images that had too many abstractions, or images that also contained people, images that had multiple animals, so things like that. So I chose what I thought would be easiest to learn from, to learn what a dog or a cat looks like, and actually obtained a much better result there. So this is something that, of course, will not help you if you have a certain label set and that's all you have. However, if you are in a position when, for instance, you have unlabeled data and then you have a limited budget for labeling, perhaps you could manually pre-screen your data just to make sure that the data points that you choose to label are representative in some way, if that's possible. Now, the second moral of the story is something that was very unexpected to me and was very frustrating at first. So you know how in the theoretical part I talk about how we just take the classifier and we add an extra fake class to it, and this is going to be our new discriminator. So again, in theory, this is what we do. Of course, if we do it in practice, if we just add an extra logit, it does not work at all. And what I mean by it doesn't work is it does not give us any increase in performance over the supervised model. So apparently, instead, what we need to do is we need to keep the number of output logits the same. So for binary classification, we had 2, and we keep it at 2. We don't add the third one. And instead, what we do is we change the loss function. So here I have the expression for the loss function. Again, I won't get into it too much, but if you want to know where it comes from, it is discussed in both of these papers, I believe. So basically, the idea here is that even though we have, let's say, 2 logits, normally, in the end, when we adapt the probabilities for the 2 classes, they would add up to 1 because the image has to be one of the 2. However, with this new loss function, they the loss function can go from basically 0 to 1. So it could be one of the two classes, or it could also be none of them. And then, of course, if your image is none of the real classes, it means that it is fake. So effectively here, you have added a new class to your classifier, but you have done so without increasing the dimensionality of the output layer. Right, so here the idea is to output a strong class prediction for the real examples and small class predictions for the fake examples. So if you're not sure, you're saying that it's fake. So I think we are nearing the end. Yes, we are actually. So here's the only French word that I have in my presentation. Merci. Merci pour votre attention. And if you would like to follow me on LinkedIn, I have a link here because I tend to blog quite a bit. So I like to blog about these kinds of things, and I typically post my links there. So thank you for your attention. Mm-hmm. Mm-hmm.
Okay, so thank you very much, Olga. We're going to open the question section right now, and when there are questions, I'll read them out to you. And once again, thank you for this talk. It was very clear, very interesting.
Thanks.
So, Olga, we have one first question from Cécile Huybonroy. Thank you. I didn't catch the GitHub URL. If you could please share it.
Oh, sure. Yeah. So it is Olga Petrova, semi-supervised PyTorch GAN. That's a long one.
Thank you. Well, that was a very specific question. You were very clear then. Thank you very much, Olga. Thank you once again for closing this DataXDays series, a series of 17 fascinating talks about data spread out all along the month of June. So for those listening, don't hesitate to watch again our videos on replay on our YouTube channels. You can also share them. And it would be of great help to us if you could fill in the Q&A linked in the YouTube comment section to help us prepare next edition. And see you next year for the DataXDays 2021.
Thank you.
Thank you very much. Bye, Olga.
Bye.